Hello, everyone, and thank you, Hari, for inviting me and Optima for hosting me for this event. It's a pleasure to presenting genetic programming and evolutionary intelligence for, I think, audience not only all over the Australia, but all over the globe. And I hope you find this presentation useful. And I think now in the era of data analytics, AI, and big data, it would be helpful and interesting to you. The topic of my presentation is evolutionary intelligence for predictive data analytics. And if you're familiar with evolutionary intelligence or evolutionary computation, you know it's somehow huge area. But here, I specifically in this presentation, I focus on how we can use evolutionary intelligence for predictive analytics, and I specifically talk about genetic programming. So before even going to detail, let's talk about the big names and who the people who has the most contribution in this area. First, we can go back to evolution philosophy, which discussed in 13th century by Rumi, also known as Maulana. For example, in one of his poems, he said, "Az jamadi mordam و nami shudam, و az nama mordam ze hayvan sar zadam, mordam az hayvani و adam shudam," which means I died as a mineral and became a plant. I died as plant and rose to animal, and I died as animal, and I was a man. And he believed in evolution in some sort of Darwinian sense, which you can find it from this poem and some others. The theory of evolution, of course, came from the Charles Darwin, and particularly from his well-known book published in 1859 on the origin of species, which was discussed evolution based on natural selection. And when we talk about data analytics and machine learning, we should also pay respect to Alan Turing, who also discussed evolutionary and genetic search. As you can see, I quoted from one of his papers published in 1950, the paper called Computing Machinery and Intelligence, and he said there is a genetic or evolutionary search by which a combination of genes is looked for, the criterion being the survival values. So speaking of evolutionary computation, probably you know it's very popular for optimization purposes, and particularly for multi-objective optimization, when the mathematical optimization cannot handle those problems, we usually go toward evolutionary multi-objective optimization. So evolutionary optimization has some overlap with natural computation, have some overlap with machine learning, overlap with AI. And in one of our recent papers, which I listed here, we discussed how evolution can help us in order to do data analytics, how it can address challenges in machine learning. And we discussed it in several different contexts. If you are interested, I refer you to this paper. But as I already mentioned here, we only focus on evolutionary computation in predictive data analytics. First, let's discuss the outline. So the outlines are two main parts. First, I'll talk about genetic programming and some of the advances in this area. And the second part, I will discuss about how genetic programming can be used for big data analytics. This is actually one of the big challenges. So in the genetic programming part, I will briefly introduce genetic programming, some of the advantages and distinguished features of genetic programming will be discussed. And then I will discuss team solution, multiple regression, how genetic programming can be hybridized with multiple regression. And in the second part, I will discuss two approaches I propose for using genetic programming for big data. One of them is called multi-stage genetic programming, and the other one is combining information theory and genetic programming. So speaking of predicting data analytics too, generally they are divided in two classes: statistics such as regression and AI-based method. Probably you heard artificial neural network, deep learning, fuzzy logic, support vector machines, and genetic programming is also another AI-based predictive analytic tools. But if someone asks, what is genetic programming? Generally, my answer is it's software when the evolution is the programmer. So I borrowed this interesting figure from COSA's website. So this exactly explains what I'm talking about. So genetic programming actually can be applied in so many different problems based on the definition I gave you. Software when evolution is the programmer can be applied in so many different problems. Actually, COSA in one of COSA proposed genetic programming in the 90s, and in one of his book, I remember he listed more than 80 genetic programming applications. So one of them was regression and data analytics. The rest was other sort of problem, like a sorting and other problems. So it's interesting, and if you would like to know more about genetic programming, I really refer you to his book series called Genetic Programming. It starts from Genetic Programming 1 to Genetic Programming 4. And also he has some movies. And I think last year, John uploaded those in YouTube. So they are very easy to access if you're interested. But as I mentioned, genetic programming has so many different applications, but the most popular application for genetic programming is data analytics, or more specifically predictive data analytics for a problem like regression, classification, and time series. But what is genetic programming? So genetic programming, it's following the Darwinian natural selection. And it creates programs, computer programs, in order to find relationships between inputs and outputs. So like any other evolutionary strategy, it has an iterative process, which we call it generation. And during this iteration, we apply evolutionary mechanisms such as selection, crossover, and mutation. Inspiring from Tree of Life, they usually represent genetic programming using these tree structures when it has some terminal nodes, which could be variables or constant numbers, and a functional node, which could be a mathematical operator or logical operators. And this is the representation that have been traditionally used for genetic programming. Now, crossover could happen between two trees. For example, we can borrow some features from each parent and create a child. And mutation, we can make some random changes or semi-random changes within the program and call it mutation. But before moving forward, I really like to address what are the distinguished features of genetic programming, because there are so many other predictive data analytics out there. But why we say genetic programming and why we need to bother to go to another new method. So the first and one of the main features, or to me, the best features of genetic programming is that it can find a structure. So if you, for example, NASA used it about 15 years ago for designing their ST5 mission communication antenna. So this is a well-known case study for genetic programming when there are so many engineering designed antenna, but genetic programming could find the best structure and outperform all those engineering design antennas. And if we look at it from a data analytics perspective, for all other machine learning techniques, we need to define the structures. Such as, for example, if you work with neural network, we need to define the number of layers, activation function, number of neurons, etc. But genetic programming starts from scratch, and it doesn't need any predefined model. We only give the mathematical or logical operator to it, and it tries to build the structure through evolution. So I listed its features here, such as the structure can be found using evolution, predefined structure is not defined, and this is the feature that distinguished genetic programming from other machine learnings. And we do not need to have any prior assumption. Of course, embedding knowledge in the system help, but basically it doesn't need if you don't have any of those information. The second and very interesting features of genetic programming is its simplicity. We usually try to control the simplicity, but in general, it's relatively short and simple in compare with other machine learning or data analytics tool. For example, one of the good studies that I found is a study by Kelly and Malcolm. They used genetic programming for Ottery game in 2017, and they found these structures using genetic programming. And actually, this is one of their cases. There are so many Ottery game solved in their paper, and this is one of the GP models proposed. And it could outperform deep learning using this simple structure. And deep learning for this case had thousands of hundreds, I think 800,000 coefficients to be optimized. So we can see how complex was the deep learning, and still genetic programming could outperform deep learning in one of the deep learning strengths, which is Ottery game playing. And actually this raised a very philosophical questions. Do we really need all the time to go to the very complex deep learning, or we should try some simpler model like genetic programming? And actually this study followed by another study by Wilson et al. They also got a very good results in 2018 for Ottery game. They again could outperform deep learning using another genetic programming. And actually based on that, MIT Technology Review came up with an article, and it was very nice to see that when they said evolutionary algorithm outperform deep learning machines at video games, and they said neural network have gained all the headlines, but a much more powerful approach is waiting in the wing. Another inherent feature of genetic programming is that it tries to select, make the big selections during this evolution process, actually during the training process via evolution, if I want to be more accurate. For example, in data analytics, we need to do two big selections, feature selection and model selection. So for features, we need to find an optimum number of features as it's visualized here to gain the most accurate model, and also which usually happen after pre-processing, etc. And then we need to find the best model, the second selection. So this is another big selection need to be made in data analytics. But as I said, genetic programming inherently select the features during the training process, and also it doesn't have any predefined model. Yes, so basically it doesn't need any model selection. The structure and model will be built during the generation. And another distinguished features of genetic programming is that it's a population-based algorithm. So it can be easily parallelized, and that's, I think, what most people who does evolutionary computation take advantage of it these days. So when we have this population, we can simply put this population in the parallel processing. And we can take advantage of the era of cloud computing, distributed system, and these new powerful parallel processing systems. So after these advantages, I would like to explain some of the application with some real-world problems. But I should say, because of my background in engineering, most of these case studies comes from engineering, and I hope you find them helpful. So the first case study is predicting the maximum roof drift of a complex structure under earthquake. So first, looking at the structure, I should say it's a very complex structure. It has some special elements such as these post-tensioning bars and this lateral load-bearing element or energy dissipation element. And this structure can actually rock during earthquake. As you can see, the column can uplift from the base. So the structure itself complex. And when it's under earthquake, and earthquake itself is a very stochastic process, yes? So under earthquake, we want to predict the maximum roof drift of a structure. For example, here I used Manjil earthquake, and this is the maximum roof drift of this structure. So you can see how difficult this problem is. So based on the problem definition, I should say we have two different class of variables: structural design prompters such as geometrical and mechanical prompters, and also earthquake intensity measures. So there are so many of them out there. I look at the literature, it's more than 30 of them out there, but I selected the 14 most popular here, so I somehow shorten and reduce the dimension for this problem. So the prototype structure I studied for this problem is the office building designed for a stiff soil site and located at LA, California. And this is the SCCBF system that I'm going to study. And 3 elevation considered here: 4-story, 6-story, and 8-story building. And I designed 75 different structures and applied 170 earthquake to each of these structure in order to create a comprehensive database. So I created database, but there's one big problem. There are so many intensity measures. So I wanted to somehow select some of those features and reduce the problem dimension. So the simplest way of looking at the features is looking at correlation coefficient of each feature and the output. So I look at the correlation coefficient simply to see which variable are the most correlated with the output. But the problem in that case was that this problem was highly nonlinear. So we have very, very difficult and highly nonlinear problem. What I did is I improved correlation coefficient, actually modified correlation coefficient with genetic programming function, and I call it evolutionary correlation coefficient. And now this is another function for correlation coefficient, which also can somehow represent nonlinear relationship between two sets of data. And I put it into practice for this problem. These are the earthquake intensity measures, and this column is correlation coefficient, and this column is evolutionary correlation coefficient, which also considered nonlinear relationship between two sets of data. And as you can see, we have a very good improvement, and in some cases more than 200% improvement, and in some cases more than 300% improvement happened for these after using evolutionary correlation coefficient. So then I try to select the 3 best features based on this analysis, and I run genetic programming. And I should say, for genetic programming, what we usually do is defining 2 objectives. One of them is accuracy, the other one is complexity. And then we try to come up, put all the solution in a pool and come up with the Pareto front solution. And eventually we select one model, mostly come from this area. Because after here, the complexity increased without that much improvement in accuracy. So eventually I selected this model as the final multi-objective genetic programming model. And these are the simple formula for this problem. You can see, considering this is having such a very stochastic and complex problem, predicting it with such a simple formula was very worthwhile. I remember my collaborator was very happy about what we did and the equation we obtained for this study. And these are the predicted versus experimental. You can see the prediction seems very accurate with around 97% correlation coefficient. And actually this study recently accepted at IEEE transaction on industrial informatics, but I haven't got the final citations to put it in here. And another complex engineering problem that engineers are dealing with is inverse analysis. So I should say, in engineering, when we have a forward analysis, which means we have the system, we apply input, and it gives us output. Very simple analysis, and it's usually formulated for most engineering problems. And finite element simply does forward analysis. But how about inverse analysis? If we have an input and output, but we don't have the system prompted, This is called inverse analysis, and it's a very difficult problem from engineering perspective. So I'm going to show how we apply genetic programming for this case. So this is the framework here on the left-hand side, proposed by Professor Qaboossi long time ago at UIUC. He suggested when we have an unknown constitutive model, what we can do is run two parallel finite element analysis, one of them force control, the other one is displacement control, and we try to converge the system parameters of these two finite elements. And based on that, he developed a stress-strain database and train a neural network model. And he put all of these systems in a loop. So try to every loop improve this artificial neural network model. But when I look at this system, actually the system is very interesting. You have an unknown material, you can develop a neural network constitutive material model for it. But there is a big restriction after here, because how we can use this very complex and sometimes black box model in practice. For example, how we can use it in a general purpose software, finite element software such as Abacus or ANSYS, or how we can take Jacobian matrix out of this neural network model. So what I did is simply replaced genetic programming with neural network in order to address these challenges. So I replaced neural network with genetic programming, which can be simply translated to a mathematical formula. Now we can easily take derivative from this system and form a Jacobian matrix and even use it in a finite element software. So I put it into the test. It is a cantilever beam as a case study here, actually Truss beam. So I applied some forces, and this is the force displacement curve of this system. And this is the prediction by Professor Qaboossi's framework. You can see it's very accurate eventually. And this is a genetic programming, that final genetic programming model, which easily translated to a mathematical formula. And this is a prediction of genetic programming versus a reference model. You can see they are very close. So the good thing here is I had this simple explicit formula for the constitutive model. I can simply use it in any finite element software. Actually here I I use it in Abacus software. So this is the reference model when it used the Ramberg-Osgood material model. And this is genetic programming based model. And you can see they are almost identical. And the values are very close for both cases. And it seems it works very well. I simply write down in the finite element software as a user defined material, and it gives me very good and accurate results. And I tested for other cases such as soil modeling or Arctic modeling, and it seems it works very well for all those cases. Another advantage of, we can also take advantage of actually population of solution in genetic programming. This is not a new idea, actually. Bramier and Banshoff suggested it in 2001, and they proposed some ways of combining these models. So this is very good. We come up with a population of solution, and we evolving all population during iteration. So why not take advantage of those whole population instead of only focusing on the best model. So actually, I put it on a test in one study a long time ago, actually 2009. So it was a prediction of flexural resistant initial rotation, stiffness of steel joints. So 3 steel joints studied here. You can see the shape of the joints. And this is the final results. This is the genetic programming with single solution. This is the genetic programming with team of solution. I think we use the best 20 models in the population, I think, or maybe 30, I'm not sure. And this is a European code for this problem, and this is a genetic programming with simulated annealing. So you can see this team solution in nearly all cases outperform others. And it gives us very, very interesting perspective that we should focus more on team solution. And of course, this is the results on the testing data, not training data. And speaking about take advantage of a team of solutions, I should say people also try to combine those solutions using machine learning or multiple regression, which is actually the most popular hybridization with genetic programming. Actually, one group in Europe proposed multi-gen symbolic regression in 2010, and one group at MIT proposed another system in 2014, and they both seem to work very well. So we can take advantage of regression and the whole great literature behind it and use it to connect the different genes in genetic programming. And this is one of the studies that I also done with hybridizing regression and genetic programming. So this is a very complex engineering problems, concrete prediction. So there are several models out there. You can see, for example, Banzhaf, SEBFIB, GL, and I should say American Society of Concrete Institute. They all came up with very complex formula for this problem. If you look at the American Concrete Institute, it's about half a page and it's not even cover most of the cases. So we propose this simple genetic programming formula when genes are connected linearly using multiple linear regression. And eventually genetic program only selected 5 variables, and it produced the most accurate model. You can see 80% RS square in compared with others. It's a very good accuracy and also lowest error, and it almost outperformed others in nearly all cases. And this formula was really simple that we even shocked. We didn't expect such a simple formula and such a high accuracy. So genetic programming can, as I said, have been combined with a regression model. For example, in this study, we also use ARM. Actually, this is used by MIT group at the first time to fuse the models. So when we have a Pareto front of the model, we try to fuse all the Pareto front models using regression analysis. Adaptive regression analysis. So this is the accuracy of different model. You can see this fused model has the lower error and highest correlation, and you can compare it with other genetic programming model in this figure. So for this engineering case study, we also compare genetic programming with other methods such as Brooks model and these other support vector regression, lasso, random forest, etc. And you can see GP came on the top in terms of accuracy. You can see the other curve. So up to this point, I've mostly discussed about genetic programming for regression problem, but of course it can be used for other problems such as classification or time series. For classification, I can point out to this study, which we try to analyze the MOOC data. Actually, the study was interesting. They put forehand scanner on headphone forehand scanner for each student, and they, based on the signals, they try to predict if the students learn what it was taught during the class or not. So it was a binary classification problem, and we again tested GP against other well-known models such as LSTM, CNN, SVMs, and naive Bayes, and it came at the top for these problems. And of course, we used genetic programming for COVID case forecasting. This is the study we have done for India, and it got a very good attention. And it was interesting. We proposed a very simple formula in order to predict the number of cases for the next 10 days for this country. And we extended this study for 15 other countries, and it's also provided us very interesting and simple formula in order to predict the number of cases and number of deaths in different countries. So finally, I would like to talk about how we can use genetic programming for big data analysis, because genetic programming, I mentioned several advantages, interesting features, etc., but it cannot deal with big data problems, because the main reason is genetic programming also try to find the structure, yes? So the search space is really vast, it's very huge. So it's, when the data is also have these big data features such as high volume, high variety, or high velocity, is it very hard to deal with this one using genetic programming. So I should say other machine learning techniques also may have difficulties for dealing with this data, and we usually need to come up with a cost-effective and innovative way in order to handle big data. So I would like to make some examples that were very interesting to me. So now in a minute, we send more than 200 million emails. We generate 4 million likes in Facebook. We send 350,000 tweets, and we submit 2.8 million search queries in Google, and we upload about 500 hours of movies in or videos in YouTube, and all happens in 1 minute, which means in a minute that I explained all of this, now we generate this amount of data. And based on Moore's law, this exponentially grows the amount of data. So we really need, when we talk about any data analytics tool, we also need to see how we can extend it for big data analytics. So these are some of the studies that I'm doing. Actually, these are the two first phases of my ARC project. Actually, it has 4 phases, so I borrowed the first 2 phases. So the first, I suggested, like most other studies in this area, we need to do divide and conquer in genetic programming. In the big data data problem in order to solve it by genetic programming. So we need to find, because you already saw people try to define different genes and sometimes connect those genes using regression analysis, but we need to do it systematically if we want to use genetic programming for big data. And also we should have some strong initialization for GP if you want to use it for big data. So there are several different approaches. For example, for systematic divide and conquer, we recently published a paper of how information theory can do it for us. So we look at variables using information theory, and we try to group the variables based on the shared information. The other things that we really need to do is extending genetic programming itself. So, for example, using multi-gene structure or coupling it with other machine learning, as I here presented, regression analysis is popular for this purpose. And also extending the traditional operator. So now if you go to the multi-gen system, for example, the operator need to be updated because the traditional one probably doesn't work in the new multi-gen genetic programming system. So one of the studies actually that I done more than a decade ago is proposing multi-stage genetic programming. So in this case, I simply try to solve the problem dimension by dimension. And this is the pseudocode, but simply when we have f function of all x's, we can decompose it to first function for first variable, second function for second variable, so on and so forth, and one function in order to consider interaction between variables. So simply we can run to predict the output with the first variable and then subtract the first function from the original dependent variable, and now create one function for second variable, and so on and so forth. So this is a simple strategy, but in practice seems very well, because if you look at it from that perspective, if you have a two-dimensional problem, you have a plane, and if you have a one-dimensional problem, you have a two-line to search, which is much lower search space in compared with the plane. So if you extend it to n dimension, you can see instead of searching n dimensional problem, you can search n one-dimensional problem. So this is a simple visualization for a simple problem. We compared genetic programming with multi-stage genetic programming. So this is the genetic programming convergence during 25 generation, and this is multi-stage genetic programming convergence during 25 generation. You can see how fast it can converge and even to a better solution. So this is a one case study we solved with genetic programming. It was multi-stage genetic programming for classification. We want to predict soil liquefaction, which is a complex engineering problem. We want to see if the soil is liquefied during high pressure or not, well, mostly during earthquake. So this is the approach we take. This is the first step. First stage, second stage, and this is the last stage with interaction. And these are the multi-stage genetic programming with interaction and without interaction. And it compared with 3 well-known genetic programming approaches. And you can see it is very competitive in compared with these 3 approaches. And we also applied for regression problem and compared multi-stage genetic programming, and neural network. We can see it's highly competitive and could outperform these 2 methods. And we also use it, of course, for time series analysis. We hybridize this multi-stage genetic programming with lasso, and it also provides us very interesting results. And finally, this is the approach that we published recently. It's on how we can use information theory in order to systematically divide a big problem to several small sum problem, and then assign 1 gene to each of these sum problem in order to solve the problem. So the paper is available online. I don't go to the details and the algorithm. So the detailed flowchart can be found in the paper, but comparing with other approaches proposed up to this into literature, it found a very good result. The lowest error is the error in compared with these other approaches, such as regression, multiple regression, genetic programming, and other multiple regression genetic programming proposed out there. And another interesting thing here is now we can track each genes, track the information of each genes using this approach. So you can see during the rounds of genetic programming, we monitored all the information used in each of these genes and track those during iteration. You can see after 300 or 400 iterations, these almost converge. I think I don't have much time, so I would like to thank you and also tell you we have a group at UTS, and I'm somehow new at Australia, but we're trying to develop our group. And if you are interested, please email me, and there would be some opportunities like PhD position, postdoc, and visiting a scholar. I really like to thank all of you for attending my presentation, and here is my contact information. And feel free, if you have any question, particularly regarding GP, to reach me out, and I will be so happy to help. Thank you.